Now we come to chapter 6, module 8. In this module, we shall learn how to apply Fourier sine transform or Fourier cosine transform to solve partial differential equations. We shall consider some examples where we shall use Fourier sine or cosine transform to solve Laplace equation, heat equation and wave equation. Now we consider example 1. Here we shall solve the partial differential equation in phi xy which satisfies the Laplace equation del 2 phi del x2 plus del 2 phi del y2 equal to 0. The range of x is from 0 to infinity and y is also from 0 to infinity. The conditions given are phi at x equal to 0 is 0 and phi at y equal to 0 is small fx, and phi x, phi y all tend to 0 as root over x square plus y square tend to infinity. Here small fx is a known function whose Fourier transform exists. So we shall solve this partial differential equation. Since the range of x is from 0 to infinity, so we have to use either Fourier sine transform or Fourier cosine transform to solve this Laplace equation. Now we can see that since phi at x equal to 0 is prescribed, that is phi at x equal to 0 is 0. Since this is prescribed, so we shall use Fourier sine transform in x. The reason will be clear shortly. Let capital phi s be the Fourier transform of small phi xy, that is Fourier sine transform of small phi xy, which is given by root over 2 by pi integral 0 to infinity phi xy sine sx dx. Now we multiply both sides of Laplace equation by root over 2 by pi sine sx and integrate with respect to x from 0 to infinity. So first we note the first integral, that is 0 to infinity integral del 2 phi del x2 sine sx dx. We integrate this by parts. So first term will be del phi del x sine sx x from 0 to infinity minus s integral from 0 to infinity del phi del x cos sx dx. Now in the first term we see that as x tend to infinity, because of the boundary condition phi x tend to 0 as x tend to infinity, the first term at x equal to infinity is 0 and x equal to 0 sin sx is 0, so that the first term is 0. At this point I may mention that if we had used Fourier cosine transform, then this term would have been del phi del x into cos sx. At x equal to infinity, del phi del x would have been 0, but at x equal to 0, cos sx would have been 1 and del phi del x at x equal to 0 was the unknown function and in our boundary condition which is not given. So this is the reason why we use the Fourier transform, because phi at x equal to 0 is prescribed, that is why we use the Fourier sine transform, so that this first term becomes equal to 0, so that left hand side of the integral, left hand side integral is equal to 0 minus s into phi cos sx x from 0 to infinity plus s integral 0 to infinity phi sine sx dx. This we have obtained by integrating by parts this integral, so that we get the integral from 0 to infinity del 2 phi del x to sine sx dx equal to minus s square integral 0 to infinity phi sine sx dx. Here we have used the condition that phi tend to 0 as x tend to infinity and phi at x equal to 0 is 0. So, the integral on the left hand side, that becomes equal to minus s square capital phi s sy, since this integral is the Fourier sine transform of small phi. Using this, we see that the given PD, that is Laplace equation, reduces to the ordinary differential equation in capital phi s as d2 phi s dy2 minus s square phi s equal to 0, where y is greater than equal to 0. Also applying Fourier sine transform to the boundary condition, we find capital phi s at y equal to 0 is equal to capital Fs s and capital phi tend to 0 as y tend to infinity. Here capital Fs is the Fourier sine transform of small fx, which is given by root over 2 by pi integral 0 to infinity small fx sine sx dx. Hence, using the boundary condition for capital phi at y equal to 0, we solve the given ODE for capital phi s to obtain capital phi s as capital Fs into e to the power minus sy. So, using inverse transform formula, phi xy is given by equal to root over 2 by pi integral 0 to infinity capital Fs e to the power minus sy sine sx ds. Now, in this inverse formula, we substitute the expression for capital Fs as given here to obtain small phi xy equal to 2 by pi integral 0 to infinity fu sine su du e to the power minus sy sine sx ds. Here we interchange the order of integration, so that u integral becomes the outer integral and s integral becomes the inner integral, and also we use the formula for sine su sine sx. We obtain after simplification 1 by pi integral 0 to infinity fu integral 0 to infinity cos s u minus x minus cos s u plus x e to the power minus sy ds du. Here, instead of cos s u minus x, we write this as real part of e to the power is mod u minus x, and instead of cos s u plus x, we write real part of e to the power is mod u plus x, so that phi xy is equal to 1 by pi integral 0 to infinity fu real part of integral 0 to infinity e to the power is u minus x minus e to the power is u plus x e to the power minus sy ds du. After simplification, this gives as 1 by pi integral 0 to infinity fu y by y square plus u minus x whole square minus y by y square plus u plus x whole square du. So that phi xy finally we get as y by pi integral 0 to infinity fu into 1 by y square plus u minus x whole square minus 1 by y square plus u plus x whole square du. So, this is the solution of the given partial differential equation. Now, we may note here that if this small fu is a constant, say c, then this solution phi xy can be deduced from the above expression, although Fourier sine transform of C does not exist in the ordinary sense. In this case, after substituting Fy as C, we obtain phi xy equal to C y by pi integral 0 to infinity into 1 by u minus x whole square plus y square minus 1 by u plus x whole square plus y square du, which can be evaluated as 1 by pi tan inverse u minus x by y minus tan inverse u plus x by y, u from 0 to infinity. After performing simplification, we obtain the solution phi xy as 2 by pi tan inverse x by y. This is the solution when in the boundary condition at y equal to 0, this fx is a constant. Thus, in this example, we have learned how to use Fourier sine transform to solve Laplace equation. Next, in coming two examples, we shall see how Fourier cosine transform can be used to solve some partial differential equations. Next, we come to example 2. Solve the partial differential equation del 2 phi del x2 minus 1 by a square del phi del t equal to 0, where a square is a constant, x ranges from 0 to infinity and t is greater than equal to 0, along with the conditions del phi del x at x equal to 0 is minus ft and phi xt del phi del x tend to 0 as x tend to infinity and phi at t equal to 0 is 0 for all x in the range 0 to infinity. So, since the range of x is from 0 to infinity, to solve this differential equation, we have to use either Fourier sine transform or Fourier cosine transform. Now, here we see that del phi del x at x equal to 0 is prescribed. So, we will use Fourier cosine transform here to obtain the solution. Using the Fourier cosine transform in x, the partial differential equation reduces to the ordinary differential equation in capital phi, that is d phi dt plus a square s square capital phi equal to root over 2 by pi a square ft, t is greater than equal to 0, and here capital phi is the Fourier cosine transform of small phi, which is given by capital phi is equal to root over 2 by pi integral 0 to infinity small phi xt cos sx dx. Again, if we apply Fourier cosine transform to this initial condition at t equal to 0 of phi, we obtain capital phi at t equal to 0 is 0. Now, using this initial condition, the solution of first order ordinary differential equation is given by capital phi st equal to a square integral from 0 to t e to the power minus a square s square t minus tau f tau d tau. Now, taking the inverse transformation formula, we obtain small phi xt is equal to 2 a square by pi integral from 0 to infinity cos sx into integral from 0 to t e to the power minus s square t minus tau f tau d tau ds. Here we interchange the order of integration so that tau integral becomes the outer integral and s integral becomes the inner integral. So, we get phi xt as 2 a square by pi integral from 0 to t f tau integral from 0 to infinity e to the power minus a square t minus tau s square into cos sx ds d tau. Now, we consider the inner integral. This inner integral, that is s integral, we can write it as 0 to infinity e to the power minus lambda s square cos sx ds, where lambda is taken as a square into t minus tau, which is positive. This is equal to half of integral 0 to infinity e to the power minus lambda s square e to the power isx plus e to the power minus isx ds, x positive. We have written cos sx in this form. So, this gives half of integral minus infinity to plus infinity e to the power minus lambda s square plus isx ds after extending the integral, the second term integral from into minus infinity to 0. So, that the integral from 0 to infinity can be extended to integral from minus infinity to plus infinity. Hence, the inner integral takes this form. Now, we can again simplify this inner integral as half of e to the power minus x square by 4 lambda integral from minus infinity to plus infinity e to the power minus lambda s square minus ix by 2 lambda minus x square by 4 lambda square ds. That is, in the from the previous step we arrive at this step by multiplying and dividing by this term e to the power minus x square by 4 lambda. So, that we get half e to the power minus x square by 4 lambda integral minus infinity to plus infinity e to the power minus lambda s plus ix by 2 lambda whole square ds, which can be written as half of e to the power minus x square by 4 lambda integral from minus infinity to plus infinity e to the power minus lambda xi square d xi by taking this s minus ix by 2 lambda as xi. So, that which can be, this can be again simplified to get 1 by root 2 1 by 2 into root lambda into e to the power minus x square by 4 lambda integral from minus infinity to plus infinity e to the power minus eta square d eta, which can be evaluated as by using gamma function root over pi by 2 root lambda e to the power minus x square by 4 lambda. Thus, simplifying this inner integral, we obtain small phi xt, that is, from here, from this step we have simplified the inner integral, and so using this simplification we obtain small phi xt as a square by root pi integral from 0 to t f tau by root lambda e to the power minus x square by 4 lambda d tau. Now substituting the value of lambda, we obtain a by root pi integral from 0 to t f tau root over t minus tau e to the power minus x square by 4 a square t minus tau into d tau. Now we consider the special case when ft is a constant capital K, say. Here ft is a constant. So that in this case phi xt is equal to Ka by root pi integral from 0 to t e to the power minus x square by 4 a square t minus tau d tau by root over t minus tau. Now we integrate by parts this integral, so that we obtain Ka by root pi into minus 2 root over t minus tau e to the power minus x square by 4 a square t minus tau, tau from 0 to t plus 2 into integral from 0 to t root over t minus tau e to the power minus x square by 4 a square t minus tau into x square by 4 a square t minus tau whole square d tau, which can be written as k into twice a root over t by pi e to the power minus x square by 4 a square t plus 2 by root pi integral from 0 to t e to the power minus x square by 4 a square t minus tau into x square by 4 a t minus tau 3 by 2 d tau. Now, if we use the substitution z equal to x by 2a t minus tau, then this tau integral, after using these expressions, we obtain the second term in the inside the square bracket becomes twice x by root pi integral from x by 2a root t to infinity e to the power minus z square dz. This is equal to minus x into the error function with argument x by 2a root over t, where error function of z is the integral from z to infinity e to the power minus t square dt. So that in this case small phi xt is equal to capital K into twice a root over t by pi e to the power minus x square by 4a square t minus x error function x with argument x by 2a root t. So this is the solution for the given partial differential equation when small f is a constant. Next we come to example 3. Here we shall solve the partial differential equation del 2 phi del x2 minus del 2 phi del t2 equal to 0, x ranges from 0 to infinity and t greater than equal to 0. So this is the wave equation where the range of x is from 0 to infinity. The conditions are del phi del x at x equal to 0 is 0, phi x tend to 0 as x tend to infinity, and phi at t equal to 0 is e to the power minus x, and del phi del t at t equal to 0 is 0. X is from to infinity. Now, since the range of x is from 0 to infinity, we have to use Fourier sine or cosine transform. Since here del phi del x is prescribed at one endpoint x equal to 0 here, so we will use Fourier cosine transform. Now, multiplying both sides of this wave equation by root over 2 by pi cos Sx and integrating with respect to x from 0 to infinity, this equation transforms to an ordinary differential equation d2 capital phi dt2 plus s square capital phi equal to 0 t greater than equal to 0, where capital phi is the Fourier cosine transform of small phi and capital phi at t equal to 0 becomes equal to root over 2 by pi integral from 0 to infinity e to the power minus x cos Sx dx, which is equal to root over 2 by pi 1 by s square plus 1. This capital phi at S0 is obtained after taking the Fourier transform of this and also taking the Fourier transform of the other boundary condition, that is del phi del t at t equal to 0, we obtain del t of capital phi at t equal to 0 is 0. Here we have stated capital phi is the Fourier cosine transform of small phi, and now we solve this ordinary differential equation for capital phi to obtain capital phi st equal to root over 2 by pi 1 by 1 plus s square cos st. Hence, taking the inverse transformation formula, we obtain small phi xt is equal to 2 by pi 0 to infinity 1 by 1 plus s square cos st cos sx ds. Now we use cos s t minus x as e to the power I s t minus x plus e to the power minus I s mod t minus x, and also we write for cos s t plus x as e to the power I s mod t plus x plus e to the power minus I s t plus x, so that phi x t becomes equal to 1 by 2 pi integral from 0 to infinity 1 by 1 plus s square e to the power I s mod t minus x plus e to the power minus I s mod t plus t minus x plus e to the power minus plus I s mod t plus x plus e to the power minus I s mod t plus x ds. So, this integral from 0 to infinity can be extended to minus infinity to plus infinity. Hence, we get small phi xt as 1 by 2 pi integral from minus infinity to plus infinity e to the power I s mod t minus x plus e to the power I s mod t plus x by 1 plus s square ds. This is equal to I into residue at s equal to I by using the Cauchy formula. Now, calculating the residues at s equal to I, we obtain phi x t as equal to half of e to the power minus mod t minus x plus e to the power minus mod t plus x using the residue theorem. Hence, phi xt can be written as e to the power minus t cos hyperbolic x for x less than t, and for x greater than t phi xt is equal to e to the power minus x cos hyperbolic t. So, in this module we have illustrated the use of Fourier sine transform and Fourier cosine transform to solve some partial differential equations. With this, we complete chapter 6, and in this chapter we have learnt about the Fourier transform, Fourier cosine transform, Fourier sine transform together with their properties and their use in solving the differential equations.